there! Welcome to an A-Level Statistics edition of Math with Black Rat. Today I want to talk about conditional probability, and I want to run through two examples to show basically the gist of how it all works. Okay, so conditional probability you have met from this formula, that the probability that two events both occur, A and B, is the probability of A occurring times the probability of B occurring given that A has just occurred. You can say that the other way around, that the probability of A and B occurring is the probability of B times the probability of A given that B's just occurred. And that means that these are two ways of writing the same thing. So this is how the A-level questions evolve from the GCSE level questions, and you'll see what I mean as we go on. You learn in AS level that when two events are independent, that the AND probability is just the probability of the one times the probability of the other, and that's for when A and B are independent. And being independent means that the fact of one of them occurring has no bearing on whether the other one is going to occur, which in conditional notation means that if B is independent of A, then the fact of A occurring has no impact on B occurring, so this conditional probability is the same thing as just the event. If that's not clear at all, let me know and I'll say more on it. But I'm going to take these formulae and work from here. So the first scenario starts off a bit GCSE styled. There's a PDF of these scanned notes if you would like to follow along with the PDF, by all means, but I'm going to talk through it. Okay, so here's my scenario. I've got two boxes, box A and box B, and each of them contain marbles. There's red and green marbles in each box. I don't know why we do this, we just do. So there must be like some mathematical supply company that sells boxes and marbles, and you can order a catalog, and I don't know, I'm not on the mailing list. Okay, so in box A I've got 7 red and 3 green marbles, and in box B I've got 5 red and 15 green in box B. Okay, and I'm going to choose a marble. So first what I do is I choose one of the boxes at random, and then I stick my hand in and I draw out a marble at random. So we'll say that the probability of choosing one of the boxes, it's a half for each box. Sometimes the story problems set it up differently and say you're only likely to pick the first box a third of the time, just to make it a little bit more interesting. But it should be clear from the problem. Here I'm going to say that the boxes are as equally likely as the other. Okay, but the balance of red and green marbles in each is different. So you can draw this as a tree diagram, and here it is. So a tree diagram works when you've got your first choice, and then your second choice, and then all of your outcomes. So the first thing I do is I choose a box. So the probability of box A is a half, probability of box B is a half. You know this, but we'll talk it through. Okay, then once you've chosen one of the boxes, there's two color choices. There's a red choice and a green choice, and this is where the conditional probabilities live on your tree. This is notation you learn at A level, but you were familiar with the concepts from GCSE level. Okay, so the probability of choosing a red, given that we just chose box A, 7 out of 10, 3 out of 10 for green, 5 out of 20 for box B, red marbles, and 15 out of 20 for box B, green marbles. And you've got 4 outcomes, and the outcomes are your AND in probability notation, the probability that you chose box A and you chose a red marble, and you get that final probability by multiplying the probabilities along the branch. So the probability of box A and a red marble is 7 out of 20. And we can fill all this out And we can answer some basic questions. What's the probability of selecting a red marble from box B? Well, that's 5 out of 40. What's the probability of getting a red marble? Well, there's two ways to get a red marble. You either choose it from box A or you choose it from box B. So you would add 7/20ths plus 5/40ths, and that's the probability of selecting a red marble. And I can ask all sorts of questions that are straightforward to answer off the tree like that. Okay, so I've kind of summarized that at the bottom here, that a GCSE style question is, okay, what is the probability of drawing a green marble given that you chose box A? That's literally reading it off the branch, that's 3/10. Okay, the A-level question goes the other way around. So the tree is drawn that first you choose the box and then you choose the marble. And the A-level question says, given that you've got a particular marble, what was the chance that it came from box A? Okay, so perhaps, given that you're now holding a green marble, what are the chances that it came from box A? So the conditional probability is written the other way around. And we can solve that by using the formulas, these formulas. Okay, and this is how we're going to do it. So, okay, this is some wordy bits that I've already just said out loud to you. All right, so start from what we know. Okay, the probability of box A and green. This is reading off the tree, is probability of box A times the probability of green given box A. And that means I can figure out the probability of A and green, and that's 3/20ths. You're probably ahead of me and just pulled it off the tree immediately. But here it is formally written out. Okay. Then we're going to write this and statement the other way around. I'm going to switch the conditionals. Okay, and I'm going to write it like this. So the probability of box A and green is also the probability of green times the probability of box A given green. And this is what we want to know. So I have this number, that's 3/20ths. I need to figure out the probability of drawing a green marble. I said this a minute ago, that there's two ways you can get a green. You either yank it out of box A or you yank it out of box B. Add the probabilities and you get 21 out of 40. So that's your probability of drawing a green marble. And that means we can stitch the numbers all together. And here we are. Sorry, try to make that a bit horizontal for you. Okay, so A and green, that's our 3/20ths. The probability of green is 21 out of 40ths times the conditional probability that we want. Do the fraction division, and we cough up 6/21. 6/21s, I don't know. 6 out of 21. Those are your chances. And there you go. So it's slightly less than a third of a chance that the green marble came from box A, which isn't unexpected because there's loads more greens in proportion in box B. So the chances that the green came from box A aren't that high. So it's a reasonable answer. And there's all kinds of questions like this that A-level asks. You can say, okay, here's something relevant to today's news. That suppose you have a disease that occurs with a certain frequency in the population, like, I don't know, I'm just pulling numbers out of the air. 3% of people are known to have this disease. Okay, so you know that a person either has it or doesn't, and that's the first part of your tree. And then you say, okay, well, we've devised a test, and 99% of the time it correctly identifies somebody with the disease, and 98% of the time it correctly gives a negative when you don't have the disease. But that means you're getting some false positives and you're getting some false negatives. So you can fill out the test effectiveness on the second half of your tree branches. Then you can say, okay, well, given that your test results came back negative, what are the chances that you actually are negative? Or what are the chances that you are positive? Or given that your test result, here's the scary question, oh my God, I got a positive test result. What are the chances that I actually am sick? Because sometimes the test is wrong. And sometimes that turns out to be a surprisingly high percent, even if the test looks like it picks up things quite quickly. And those are interesting problems to go through. Hit me up, I can give you examples with numbers, but I don't want to make this video super, super long. Okay, if any of this is not clear so far, please, 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 please let me know, and I'll try to say it again in a way that makes sense. Makes better sense. Okay? So that's a crash course into A-level trees and conditional probabilities. Here's another way we can talk about conditional probabilities, and that's using a contingency table. In a contingency table, here's one I made before. Okay, a contingency table is where you have numbers in a grid. So like there's a group of people and there's 2 attributes for each person. So like you have a person and they either play football or rugby, and they either come from Merthyr or they come from Newport. I just made this up out of the air. The original question was something to do with male and female, and I just don't feel that's necessary these days to separate out by gender like that, especially binary gender. So let's not do that. Let's have Merthyr and Newport, football and rugby, and I just made the numbers up, and here's my grid. So 10 people are Merthyr footballers, and 5 people are Newport rugby players, and stuff and things. So you can do your totals across the rows. So there's 18 people who come from Merthyr in this example, and there's 17 people who come from Newport, 13 rugby players, 22 football players, grand total of 35 people. Okay, can I read the table? Yes, I can read the table. Here's how you can ask some probability questions. You might want to write this down because I'm recording this on my phone and it doesn't get the whole A4 paper. So pause the video now, copy this down. Okay, so questions. I could say, what's the probability that you're from Merthyr and you play football? We answered that as we were reading the table. There's 10 people out of 35. Okay. What's the probability that you play rugby? Well, that's your rugby people. That's 13 out of 35 people. Okay, fairly nice to chop and group your population here to answer those sorts of questions. Okay. I could ask complicated questions like, what's the probability that you're a Merthyr footballer, or you're a Newport rugby player? Okay, there's no overlap in this example, so we add the probabilities and get 15 out of 35. Okay, that's all relatively readable off the table. Okay, you can ask conditional probability questions too, and they look like this. You could say something like, given that a person is from Newport, what's the probability that they play rugby? And in contrast to drawing probability trees, contingency tables let you read that off quite nicely. Because if you say, given that they're from Newport, you're just looking at the Newport contingent. So I asked about rugby, so that's 5 people out of 17. So the probability that you play rugby, given that you come from Newport, is 5 out of 17. And you could ask the same question, what's the probability that you the probability that you play rugby given that you came from Merthyr? Well, that's your Merthyr people and how many rugby players out of those 18 Merthyr people. Okay, so relatively tidy questions. So I want to show you how these formulas work with a contingency table. You can read a lot of the conditionality straight off the table, but I want to show you that the formulas work and all the math holds. And then we'll look at a slightly more complex question we could ask. Okay, so I could ask, this is summarizing the formulas again. Okay, I could say, all right, what's the probability that you play rugby and you're from Newport? Well, I know that there's 5 such people out of 35 people altogether, and that's looking at the table. If I follow my conditional probability formula, then I say the probability of rugby and Newport is the probability of rugby times the probability of Newport given that you play rugby. So the probability of playing rugby, there's 13 people out of 35. And the probability that you came from Newport, given that you play rugby. So we're looking in the rugby column. The probability of Newport out of your rugby players is 5 out of 13. So here's our 5 out of 13. Multiply that. The 13s divide themselves out, and we get 5 out of 35, which is what we expected from reading the table directly. So this is showing you that the math works as we say it works. And you can ask the question the other way around. You can say, all right, you can construct it the other way around. Rugby and Newport. Well, instead of saying rugby, Newport given rugby, I could have said Newport times the probability of rugby given Newport. So then the probability of coming from Newport is 17 out of 35. Given that you're in Newport, there's 5 rugby players. Your 17s divide themselves out and you get 5 out of 35 as we expected. So that's very, very reassuring mathematics. Okay, and you can ask questions like the probability that you play football given that you came from Merthyr. Again, read it out of the tables, chase the math through. And you're a division now to figure out the conditional probability. You should take a minute and convince yourself that I've set this up correctly. Excuse me. So I'm using the formula, pulling numbers off the table, and football given that you come from Merthyr. Yeah, 10 of your Merthyr people play football. And it comes out as you expect. So this is quite nice to play with just to convince yourself that the formula works and you can read the contingency table and stuff and things. So here's the fancy question to ask. Okay. Okay, there it is in view. Okay, so suppose I pick 2 people from this pile of 35 people. Suppose I pick 2 people at random. And I'm assuming that as soon as I select one person, then the next person is a choice out of 34 people. I'm not replacing the person once I choose them. Okay, I do want 2 distinct people. Okay, suppose I pick 2 people at random. Given that the very first person I chose happened to come from Merthyr, what is the probability that both people I choose play rugby? And to look at it with first glance, it sounds like a really complicated question. And you know what? In many ways it is. Probability can get really complicated really quickly. And I don't think it's an obvious subject. I don't think it's an easy subject. I think there are portions of it that you can learn and get comfortable with. And if you ask questions that are in that nice shallow end of the pool, everything's quite satisfying. But it's easy to ask a real biter of a question. And I find that the complexity, like it goes simple, 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 depths of complexity. That's how I feel about probability. So if you find yourself, and I have a master's degree in this stuff, you know, if you find yourself going all cross-eyed at probability questions, it's because it's not a simple subject, and it's for minimal effort you can make a question very, very complicated. Okay, but the saving grace with studying at A-level is that the questions that A-level books and exams ask, even if they look weird, we're still in the safety of the A-level playground. So there's a way to solve it with the tools that we have. And I find that very comforting sometimes when I look at a question and I'm like, what are they asking here? Okay, so my route through this question was to read the words very carefully. And the words here to be careful are given that. Okay, so you've got, you know what, I'm just going to make that blue. Given that. And that means that we are in conditional probability land. Given that the first person is from Merthyr, what is the probability that they both play rugby? And here's our notation. Given that they're from Merthyr, what are the chances that they both play rugby? And rather than scratch my head and sweat and wonder, I am going to set up the formula and rely on these equations. I'm going to directly rely on these. Okay, so if you can get yourself into writing the words into this notation right here, you can walk yourself home from the formula. And that's what I did. Okay. So the probability that they both play rugby, given that the first is from Merthyr, that's going to be the probability of and divided by the probability that the first person was from Merthyr. And you should pause and take a minute to convince yourself that this setup matches the formula that I promised you at the beginning. I'm literally plopping the words from the question into that and then shaking out the formula. And that means that I need to figure out these two numbers. Hopefully from the table I can do fraction division or grab the calculator and get a number spat out. Okay, so the probability that your first person comes from Merthyr, I did that first because that's just a little bit simpler to figure out. The probability that you come from Merthyr, that's 18 out of 35. Bang, okay. Grand. Working out the probability that both people play rugby and the first is from Merthyr, that took me a bit of further thought. And I thought of it like this. There might be other ways to think about it. This is how I thought about it. Try to keep that horizontal, sorry. Okay, so the and. Both play rugby and first person from Merthyr. Well, there's two ways that this can happen. The first person is Merthyr Rugby, because they both have to play rugby, and the second person is Merthyr Rugby, or that second person could have been Newport Rugby. We know that the first person has to be Merthyr Rugby because they're both rugby and the first person's from Merthyr. I hope that makes sense to say. Okay, so two ways you can do this. It's the second person, are they from Newport or Merthyr? Okay, and because it's an or, we add the probabilities. So first person Merthyr Rugby and the second person is Merthyr Rugby. Well, that's 8 out of 35. And then you've already pulled a rugby person, so that's 7 out of 34, that you get another Merthyr Rugby person out of your pool of people. And this piece, again, your first person being a Mugby Merthyr. Wow. A Merthyr Rugby person. My goodness. A rugby person from Merthyr. That's 8 out of 35. But then from Newport, you've dropped to 34 people, but you still have all 5 Newport Rugby players. So there's your 5 out of 34. And if you run it through the calculator or scratch it out by hand, you're going to get 48 out of 595. It's not a pretty number, but that's fine. I don't care. There's our number. Okay, so we've got our numbers, numerator and denominator, fraction division. Here we are. Okay, so the probability that we want is that 48 out of 595 divided by 18 out of 35. By hand, if you like, your ultimate result is 8 out of 51. There's an 8 out of 51 chance that both will end up as rugby players, given that the first person you picked was from Merthyr. And I asked several of my math friends, friends who tutor A-level math and play with recreational math. I asked them for their opinion on this question. Could they check my method and what did they think? And one of my friends is good at computer programming and really likes to run simulations. So he knocked up a simulation. He writes in a language called Perl, but you could do this in Python or whatever your flavor is. I'm not fluent in these things, so I let him do the coding. So he knocked up a simulation where his program randomly chooses somebody out of 35 people, and if they're not a rugby player from Merthyr, they chuck it out and the program selects somebody else again. And as soon as you get somebody that plays rugby from Merthyr, because that's what you need for your first person. Then then you've got a pile of 34 people, so choose somebody at random and make a note of all the outcomes you get doing that. And then you look at the proportion of both of them being rugby players, and his numbers were coming out. Whoops, I wrote it down. Bear with me 2 seconds. His numbers for simulation were coming out around 0.156, 0.157, something like that. And that's about what that decimal is. So his computer simulation is not a proof, but it's strong evidence that the method is correct. If you want to see the program, give me a yell, and I'm happy to show that to you. Okay, I hope this sorts some things out. I hope it's a little bit more clear now. Any questions, please let me know. And thanks for watching.